Hi, my name is Soszynski and I would like to present you the mystery of the origin of long secondary periods in red giant stars. I believe that we finally found a solution to this mystery. First, let me briefly outline the basic properties of LSP variables. The LSP phenomenon has been known for many decades, almost a century. This figure from the paper published by O'Connell 1933 shows the period-period diagram for several stars, shorter pulsation period versus longer period, which is roughly 10 times longer than the pulsation period. Indeed, long secondary periods range from several months to several years, an order of magnitude longer than the pulsation periods in the same stars. This is a very common phenomenon. It can be detected in at least 30% of long period variables. The visual amplitudes of the LSP variations reach 1 magnitude, and LSP variables obey a well-defined period luminosity relations discovered by Peter Wood and labeled by him with a letter D. It's important to mention that sequence D is a continuation of sequence E, populated by closed binary systems containing a red giant as one of the components. These are eclipsing and ellipsoidal variables. This is a hint that the LSP phenomenon has something in common with a binarity. The light curves of LSP variables have a characteristic morphology different than light curves produced by radial and non-radial pulsations in red giant stars. The LSP light curves resemble those of eclipsing binaries, however with very wide eclipses. The radial velocity curves of LSP variables are usually asymmetric, non-sinusoidal. The full radial velocity amplitudes range from 2 to 7 km per second, with a clustering around 3.5 km per second. Assuming the binary explanation of the LSP phenomenon, it would correspond to the brown dwarf or a very low mass main sequence star companion. It's time to discuss possible explanations of the long secondary periods in red giant stars. Here I collected potential explanations of the long secondary periods considered in the literature. In the recent years, two of the most favored explanations have been discussed: convective non-radial pulsation modes and binarity. I try to convince you that the binarity is the final answer. Of course, a brown dwarf companion itself could not be the cause of such large amplitude light variations that are observed in some LSP variables. These 6 figures from 6 different publications show results of simulations of stellar wind in closed binary systems containing AGB stars. All these figures show basically the same pattern: a spiral cloud of dust around and behind a companion of the AGB star. Such a cloud should obscure the red giant star once per orbit, causing the LSP variations. Additionally, the cloud should absorb the stellar radiation over a wide range of the electromagnetic spectrum, and this energy should be re-emitted at the infrared wavelengths. Our new results are based on 2 sources: optical light curves obtained by the OGLE survey and infrared data collected by the WISE Space Telescope as a part of the NEOWISE mission. Our procedure was as follows. We selected about 16,000 well-defined LSP variables in the OGLE databases, and we cross-matched this sample with the NEOWISE archive. The typical NEOWISE light curves contained only 12 epochs, but fortunately, regions around the ecliptic poles are observed much more frequently due to the polar trajectory of the WISE satellite, so finally we extracted several hundred large amplitude LSP variables with well-sampled infrared light curves. And this is the result of our analysis. Light curves of 8 selected LSP variables. These blue points are optical ogle light curves. These orange and red points are infrared neowise light curves. The most striking feature that distinguishes infrared from optical light curves is the presence of the secondary minima that can be interpreted as secondary eclipses that are visible only in the infrared range. This feature proves that the physical mechanism responsible for the LSP modulation is the obscuration by a dusty cloud orbiting the red giant with a substellar or sterile companion. As the companion, shrouded in a comet-like extended cloud of dust, passes between us and the red giant, we observe wide primary eclipses in both optical and infrared light. When the cloud and the companion then pass behind the star, we observe secondary eclipses at the infrared wavelengths only. To explain the large fraction of red giant stars with brown dwarf companions, 30% of bright red giant stars, it should be assumed that these objects are former planets that increase their mass accreting material from their host stars. It means that long secondary period variables could be the tracers of the extrasolar planetary systems. And this is my last slide showing the on-sky distribution of LSP variables in the large and small Magellanic Clouds. If we are right, it would be also the spatial distribution of extrasolar or actually extragalactic planetary systems in the Magellanic Clouds. Thank you for your attention.